Hi, welcome to the Noise Path. I have another unusual episode for you guys. We're going to take a look at this NordicTrack bike, which we bought about 2 years ago. Now, this entire bike is controlled from an Android PC in the console, which sits in the front of the bike. And without this console, you essentially cannot use the bike because the resistance, the RPM, and all the statistics are controlled from this Android PC. Now, our PC has died on this bike, essentially rendering the entire bike useless. Now, I did call NordicTrack after waiting about 3 hours or so. Eventually, they told me that the bike is under warranty, but the labor is not under warranty. So if I pay some labor, someone's going to come and take a look at it, and then they're going to give me the parts to fix it. So I did pay for that. It was $150 or so, and indeed they came and told me, yep, the Android PC is dead. We're going to have to replace it. But then when it came to ordering it, they told me they were mistaken. The bike is not under warranty, and they want about $1,000 to replace this console. Now, I'm not about to pay $1,000 for this. I also think that that's not very good practice for changing your mind after you've told the customer something. So, well, we're engineers. We can just fix this problem ourselves. We can get rid of the PC altogether and build our own software and hardware, much simpler, but to control the bike and bring it back to life so we don't have to get rid of it. So, let's give it a try. And here's what's inside of the console. So the goal here is to use the console's frame because it fits on the bike and use as many components inside of it as we can to control the bike itself. So we have a little board over here. It has its own little microcontroller in there, and this essentially controls the speakers and a few other functions over here. But all the brains of it, everything that runs and controls everything ultimately is actually inside of this display, which is an Android computer. And it has a USB interface. So the only thing this Android computer produces is a reset switch, which is useless, the audio coming out, which is amplified by this board and then fed to the speakers at the top, and then of course the 12 volt going in. So this entire computer is useless. Once it's dead, there's essentially nothing you can do, and there's no way to reprogram it, and of course they don't help you at all. So we have to throw that away essentially. But the speakers are, yeah, I guess you could play speakers through it, but if you have an iPad, you don't really need any of this. So it looks like the most valuable thing are actually these interface connectors, because that allows us to very cleanly connect the rest of the bike to this, so we can bring those signals in and build our own little board over here and our own little display to control the measure the resistance and control the speed and all those things that enable the bike to actually have anything interesting other than just sitting there and pedaling it. The resistance, controlling it and figuring out how much calories you're burning are the most useful pieces of information. There's over here for volume control. This is what controls the fan. There's a little fan in there that blows air at you, not really super critical. And there is some headphone jacks and everything else over here. So I'm going to take as much of this out as I can because we don't need it. And then we can take a look at this board closely as well. We can also take a look at the power supply board that's inside of the bike because we don't need that neither. But the power supply and this talk to each other through these connectors at the top. Now, all of that has to go, but this is a good start. And here's what's on the side of the bike body after I've made some modification. So this board used to be here. This is yet another board. This is actually a power supply board, and it has another microprocessor on it with a serial communication to the console, another board that we were looking at. So this whole thing is ridiculously over-engineered. I'm guessing that they just kind of put it together because they could, but I certainly wouldn't have designed it this way. So I took this board out since we have no control over this. We don't know what software it runs, and we're going to build everything ourselves anyway. So I used another power supply in its place, essentially fitting into the same cavity it used to sit on. And I used all the cables that used to go to the console, and I just wired everything that I needed to that cable. So I just bypassed essentially everything, passing all the functionality to the front of the bike, where I'm just going to use a single microprocessor to control everything. Luckily, there were enough cables for me to do that. I had to make some compromises and simplify some things, but I think it's going to work just fine. Now, this bike also has elevation control, which is a bit of a gimmick. We don't really use it, so I'm not going to wire it up. Nothing to worry about there. So I only am going to essentially measure the RPM of the bike as well as adjust its resistance, and all the calculation can be done somewhere else. If you look carefully, you can see that over here, there's actually a reed switch right there. And that reed switch passes in front of a magnet. There's a magnet right there. So when that magnet passes in front of it, you get a pulse from this reed switch. And that's how you can measure the RPM, because there's one magnet, and when it makes another half a rotation, there will be another magnet that passes in front of it. There it is. And that's going to mean that you've done half a rotation, and from that, if you measure the timing, you'll find out what is the rate in which you're pedaling. But pretty straightforward. This is how essentially all RPM systems work. Now, in terms of adjusting the resistance, what we have is a metal plate here. So this is the metal wheel. It's quite heavy, has a lot of inertia in it, but it's also very conductive. So what they can do is they can bring two magnets, which are inside of this, around the two sides of this. And what happens is that when you bring two very strong neodymium magnets on these moving plates, you're going to create eddy currents in there. And those eddy currents are going to resist back the movement of the magnet over the metal. This is a very common phenomenon. And in fact, if you turn this into a superconductor, you can actually float those magnets, which is a totally different story. So the more the magnets is overlapping this metal piece, the higher the resistance you will feel and the harder it would be to rotate this wheel. So that's how they adjust the resistance. There's no contact actually, so it's done all frictionless, just using magnetic fields, which a lot of other bike manufacturers also do. Now, in order to move this back and forth, they have a motor over here. And this motor itself is also really simply put together. So there's a little arm attached to it. So when this motor rotates, this plate can come down and you can adjust the resistance. So this actually has 5 wires coming out of it. And it's really, really straightforward. 2 of the wires goes into the motor. So you spin the motor one way or the other way. It moves the plate up and down. And the other 3 go into the 3 terminals of a potentiometer. So this is basically a servo in open loop. So what I've done is that I've removed all these unnecessary parts. I'm just going to pass the analog voltage generated by the potentiometer by putting 5 volts across these 2 other terminals, pass that to the front and use the software to close the loop, which is what they were doing before too. You need some software to close it. So you need to digitize the value of the potentiometer, write some code around it, and then you'll find out exactly the location of this. You're building a software control servo, and then you can adjust the resistance based on that. So that's all the changes that I've done here. Now let's take a look and see what happens to, what kind of PCB do we need to take advantage of all of these things. We have 5-volt supply, we have the read connection, we have the analog voltage from the servo, we have the motor control, the motor itself going there. All of it is going to go to the front console. Now we need to put together a system to control it. And here's the back of the LCD screen itself. So we have, of course, the LCD controller as well as the touch panel interface, which it connects to the rest of the display. Now there's nothing more in there than just this. There's just one board, and that's surprising because you don't need a lot of PCB for an Arduino computer. There's a little camera in here as well, and a microphone because you can have live classes and so on, which we never used. And by the way, I do have a Pi hole installed inside of the house, and this was one of the biggest offenders of tracking and trying to send information to advertisers, which it wasn't supposed to be sending essentially. But anyway, that's a different story altogether. That's what you get from these devices anyway. And here are all the boards that are inside of this bike. We have the main power supply board, which is in the body of the bike. Now the AC line comes over here. This acts as the main power supply for everything. And it has its own processor, which talks to this other board with an RS-485 interface throughout the bike. And then this guy talks with the USB to the Android PC on this board. This is just, again, too much complexity for no reason, but I guess they can mix and match these for different models, and it's just easy to connect them together because the interfaces become so standardized. But we're going to get rid of all of these. Of course, we don't need any of them, but it's interesting to see how the architecture of the bike is. Now, when it comes to our custom circuit, there really isn't much to do because all we want to do is to control a DC motor in order to set the resistance and read the potentiometer voltage so we can essentially make a servo. We also want to control an LCD screen so we can display our statistics and of course measure the RPM. So in terms of modules, I'm going to use a Metro Mini, which is an Arduino compatible module that you can buy from Adafruit, and then there is also an Adafruit 3.5-inch TFT display which you can directly control from the Metro Mini, and there's a lot of libraries written for it so you can do graphics fairly easily. When I did the RMS meter project, I used a very similar configuration. Now we can also use a DRV8871. This is a chip from Texas Instruments, allowing you to control a DC motor in both directions, which is what we need to do to increase and decrease the resistance. As you saw, this is an H-bridge essentially, with some additional features and functionality, and a bunch of pull-up resistors, and of course the signals that are coming from the bike. So overall, this is pretty straightforward. Now there's actually a mistake in this, and I didn't realize that. I'm going to let you see if you can figure it out. You can pause the video and think about it a little bit. I didn't think about some subtle point here. Now keep in mind that the power supply coming into this entire module is 5 volts. So I just simply connected the 5 volts to the Metro Mini, to the LCD screen, and I also connected it to the driver for the DC motor. The DC motor is a 6-volt motor, but it also will work at 5 volts without any issues. What I did not consider was that the DRV8871 module from TI has some protection built into it. If you look at some of its list of features, right over here, you can see that it has under voltage lockout, and the minimum voltage is 6.5 volts. Now, under voltage lockout is a very useful feature for an H-bridge that's used for DC motor driving, because if the voltage is too low, you could actually hang the motor and it can stall, and stalling a DC motor will draw a lot of current. It's not a good thing in the system. So that's why they have under voltage protection, to make sure your DC motor gets the voltage that it needs. I didn't consider this. So of course with a 5-volt power supply, this would never even start. So I had to place a boost converter manually on the PCB that I made in order to correct for this, which we will see when I look at the board. And here's the layout of it. Again, nothing unusual, just to put it very quickly together. We're going to mill this out using the CNC machine, which I will show you in a second as well. And then we can go ahead and try it out. All right, well, we also need to write some code, of course, to control everything. And this code that I've written in Arduino is by no means optimum. I'm sure it can be improved quite significantly. I just quickly threw it together, and I can share this so you can take a look at it and modify it as you see fit if you ever need to do something similar. But I do want to show you a couple of highlights of some of the subtleties that are inside of the code, which you may find interesting. Now, the first thing is that we need to figure out what potentiometer voltages correspond to a linear field in the increase of the resistance of the bike, because they're not one-to-one. It's not a linear voltage to linear resistance, because the magnets moving over the wheel are not moving in a linear way because they're on a circular pattern, and the arm that moves it has this complex shape that goes through. So I had to basically figure it out by trial and error based on previous experience. And these are the voltages that I came up with for resistances between 0 to 25, which I just put into an array. Now we need to read buttons as the display is being updated, and we also need to be able to measure RPM. So of course we need to set a couple of different interrupts. Now I have a hardware digital bit interrupt for measuring the RPM, and I have a timer running at 5 Hertz in order to detect all the other activities and to update the screen. So here's our timer that we can set up, and this is a 5 Hertz timer. Every time this is triggered, I check for buttons and update the statistics and measure the calories and the wattage and all the other calculations that need to be done in the background. And this is the code right here that sets the resistance. Now in a DC motor, when you start spinning a DC motor, if you stop, it will continue because of its momentum for some time, making the adjustments very difficult to do accurately. So what you actually want to do is, after you spin the motor, you want to then connect the two terminals of the motor together in order to halt it. This is essentially breaking the motor because of back EMF. Interestingly enough, this is exactly the same principle that actually makes the resistance of the motor fundamentally is because of eddy currents and so on. So if you take that into account, I can just set the two H bridge to 1, and that shorts the terminals together, and that's essentially what this code does. It just checks the voltages and runs in a loop until the voltage is achieved. Here I'm updating the LCD screen, writing all the statistics out like watts and so on. We will see that in a second. And here's our interrupt handler, which then checks all the buttons and calculates all the computation every 1 second intervals, every 1 second steps. And then at the bottom over here, this thing measures the RPM. This is using the millis function in the Arduino, which measures the timing between the interrupt events. And from that, of course, you can measure RPM. And here we are making the PCB using the actual final production model of the Carvera, which I reviewed extensively on the website. This has now been released and sent to the initial backers, which is fantastic. Here it is, the software running right over there. You can zoom in a little bit here to see it do its magic. So let's take a look and see what happens when the PCB is done. And check this out, isn't that a Bobby Dazzler? I actually don't know what a Bobby Dazzler is, but whatever it is, this must be it. So here's the main frame. Of course I removed everything as you saw. I'm just using the frame because it fits nicely with the bike, and you can rest an iPad against it at the bottom here. All the cables come right through here on both sides, and they go into the circuit, which I will show you in a second. And I've disconnected everything else. We can of course put a black screen in front of it and cover everything except for the LCD, but for now this is fine. So here we have our Arduino right over here. The H bridge is here, and this is the DC-DC boost converter that I had to add in order to meet the voltage requirements of the H bridge, as I explained earlier, and of course our LCD screen and the very simple GUI that I've written. We have time, RPM, wattage, gear, distance, and average watts, and so on, the kind of statistics that you would like to see when you're biking. You can change the resistance using these exact same buttons that were on the bike earlier, which are on the handle of the bike. So I can increase the resistance, and you can see that resistance value changed right there. It does change color depending on how high you go. It goes all the way to 25 or so. And I can turn this wheel by hand just so we can get it started. And you can see we're measuring RPM, and the time starts as soon as there's activity. And if you stop, the timing also stops. Here we go, 90 RPM. Right now we're burning no watts at all because there's essentially gear is 0, so there's almost no resistance at all. And you can see also the distance is counting forward. So it works, and this is good enough to use the bike. None of the fancy Arduino requirements are there, but the whole bike has now been salvaged. And there you have it. I hope you enjoyed this quick video of resurrecting our NordicTrack bike here using our own hardware and software just so we can get it working. I really didn't want to throw the NordicTrack bike away just because there is so much carbon footprint in you manufacturing something like this. There's so much metal, so much weight, and you didn't want to get rid of it. Although I do want to welcome NordicTrack to the list of banned companies in our household. If you like this, let me know in the comment section. I'm working on a couple of review videos and repairs, which will hopefully show up. I'll see you later.